Good morning. I'm very glad to begin this second day of the seminar with this first panel. We're going to begin with this first panel. It is actually divided in two topics. On one hand, Professor from INTAM, Dr. Angel Curi, will discuss data mining. And on the other hand, he will discuss with us a topic that possibly is that might be new for some of you, different also, regarding the introduction of modern algebraic topology in the analysis of databases. What does topological data analysis has to do with the subject of the seminar? This is the analysis of very large databases. Well, that is something that our experts will explain for us. I would like to thank Elio from Infotech, first of all, for inviting Professor Curi, and also like to thank Professor Lesnick and Blumberg because they accepted to be here. First of all, in Mexico, there are really no experts on topological data analysis. So a group of us at CIMAT are trying to assemble a group that will work on this type of topologic analysis alongside Miguel Nakamura and Rogelio Hashimoto, as well as Ramon Reyes from Infotech. We are trying to make our graduate students to learn about this subject, topological data analysis. So without further ado, I would like to ask Professor Mike Lesnick to begin with his presentation today.
Thanks everybody for being here today, and thanks to Jose Carlos and the other organizers for having me. It's my first time in Mexico, and I'm definitely excited to be here. So, I work in a field called topological data analysis, and I want to tell you a bit about it today, and you'll also hear a bit more about it from Andrew later on. So, topological data analysis is a relatively new and still maturing branch of statistics. And as we think of it nowadays, it's about 15 years old, though it has a longer prehistory. And the goal of topological data analysis is to apply a very old and quite mature branch of mathematics called topology to develop tools for studying qualitative features of data. All right? Now, for this to be meaningful to you all, I need to explain to you first what I mean by data. I need to tell you what I mean by qualitative features of data, and probably I should say a few words about topology for those of you who haven't encountered it in your studies. So I'm going to do all of that in the next 30 minutes. Okay, so first, what do I mean by data? Of course, data means many things to different people, but for us, data typically means two things. First, when we talk about data, we often are talking about finite sets of points in n-dimensional space, in Rn. Okay? And more generally, we can talk about finite sets of points sitting in some reasonably nice space, or even any set of points that has some abstract notion of distance between points. All of that is fair game for us in topological data analysis. And we call such data point cloud data. So for example, here on the slide, I have a point cloud data set sitting in two-dimensional space where I have a large sparse ring of data and a small dense ring. Okay? So another type of data that we're interested in this field is functions. So we can consider a function as some data object. And we're interested in functions in particular that take values on the real line. We're interested in functions whose values are real numbers. And the domain of the function for us often can be pretty much anything. We're also interested in functions that take values in n-dimensional space for n greater than or equal to, for n greater than 1. But in our world, often the primary case of interest is R-valued functions. Okay, so this is what I mean by data, point cloud data and functions. All right? So then what do I mean by qualitative features of data? Now, informally, what I mean when I say qualitative features of data is coarse scale, global, geometric features of the data. And you might say to me, well, you're defining an unfamiliar term in terms of other unfamiliar terms. And I'll admit that I am doing that, but hopefully this gives you some intuitive sense of what we're talking about here. But to better explain what I mean by qualitative features of data, I'm going to show you some examples. So let's begin with several examples of the kinds of qualitative features of point cloud data that we consider in topological data analysis. And I'll show you examples in 2 dimensions just because it's easy to draw things there. But analogs of these kinds of examples live in higher dimensional space as well. Okay? So first example, and many of you may have encountered this example in your own studies of data, is clusters. So here we have a data set that, as you can see, breaks up into 3 distinct clusters. And we'd like to be able to detect the number of clusters, partition the data into its distinct clusters. And we want to be able to do this sort of thing even when the cluster structure of the data is corrupted by some low-density noise. Now, I should say that this problem is not one that topological data analysis is the first to study. To the contrary, this is an old and well-studied problem in computer science and statistics, and people have a lot of algorithms and methods for dealing with this. But nevertheless, topological data analysis has brought some new and interesting ideas to the problem. And we consider this part of our domain as well. Okay, so, a second type of qualitative feature of point cloud data that we consider is cycles. So here we have a data set sitting in 2D space with a cycle. It's got a hole in it, right? We're very interested in studying this kind of structure in data. And we want to be able to do it, again, even in the presence of noise corrupting that structure. Third, we're interested in tendrils or flares in data, as depicted here. So here I have a data set with a central core and 3 tendrils emanating out from this central core. Again, we want to be able to detect these tendrils, and this guy is, I'm going to have to figure out how to work him so that he doesn't move twice every time. So, yes, we want to be able to partition the data into its tendrils and see this structure, okay? So a fourth kind of feature of data that we want to study in this world is graph structure. So here's a data set that looks like a discretized version of a graph embedded in 2D, right? And if data has this kind of structure where it's sort of like a finite sample of a graph, maybe with a little bit of noise, we want to be able to see that. We want to be able to recover the underlying graph accurately, okay? So let me also talk for a minute about qualitative features of functions, okay? So we can generally define analogs of the features that I've shown you for point cloud data for functions. So the analog of clusters for R-valued functions is modes, right? These are just the peaks of a function, right? So here's a function from the real line to the real line with 2 peaks. We want to be able to see this kind of structure. And we'd like to be able to detect it robustly, even if the function had some kind of noise to it. We want to be able to see this kind of structure, okay? And an analog of the cycle in the data is what I might call craters in data. So here's an example of a function from R2 to R that's got a crater. Its graph looks like a volcano. We want to be able to see this type of structure. Okay? And I can show you more examples if I want, or I could show you, but anyway, I hope that gives you some idea of the kind of coarse scale geometric structure that we're interested in seeing in this world. This is what we're trying to get at in data. So specifically in topological data analysis, we seek to develop first formal definitions of such features, formal mathematical definitions. Second, computational tools for detecting and visualizing such features. And third, this last part is important to us, when the data is random, as it often is in practice, we want methodology for quantifying the statistical significance of such features. And Andrew is going to give, I think, a whole talk on that same topic just after me, so you'll hear more about it later. Okay? And we especially want to focus on tools suitable for high-dimensional point cloud data, data that sits in big spaces, or maybe doesn't sit naturally in a space at all and just has a metric on the data. This is the kind of data, people talk about big data applications all the time nowadays, and we have this preponderance of data in our world. And when this data comes at us in scientific applications, it often takes this form. It doesn't sit in 2D, it sits in giant spaces. So we want tools that can work there. Okay? So that's the game that we're trying to play. Okay? So now a short philosophical aside. Why do we want to study qualitative features of data in the first place? Why is this something that we should spend our time thinking about? Well, my brief answer to the question is this. The key premise behind this work, and really the key premise behind research in unsupervised learning in general, of which this is a part, is that insight into the shape of scientific data has a good chance of giving insight into the science itself, which generated the data. So if we can understand the shape of the data, the geometry of the data, then we can understand the science, hopefully, right? So anyway, my feeling is that this premise is one that experience has shown out, bears out in practice. So let me show you one example that I think is a nice illustration of this. And this is a topological data analysis example from several years ago that received a lot of attention when it came around, and I think is illustrative of what we're trying to do. Okay, so the example concerns statistics of natural images. All right? So what do I mean by natural images? First of all, when I say image, I'm talking about a digital photograph, right? So we're looking at a database of photographs, some big database of pictures. And the word natural doesn't mean that we're taking pictures of the jungle or of safari or something like this. Natural means that these are pictures that I went around with a camera. It doesn't matter if I went to Infotech or if I went on the street or in the forest. These are natural images as distinguished from random arrays of pixels. Okay? And so the question is to try to understand if these natural images have some kind of statistical structure. Can we talk about the sense in which they're different from random arrays of pixels? Okay? And so this was studied by Gunnar Carlson and several co-authors in maybe their journal paper came out in 2008, I think. And they studied a set of 5,000 3x3 pixel patches sampled from natural images, right? So little patches coming from the images that look like the ones that I've drawn over here. There's 8 of them here, okay? And so, well, let me say that because in each patch there's 9 pixels, each patch can be thought of as a point in 9-dimensional space. But if we normalize the intensity and the contrast of the pixel, then we can project these points down onto a 7-dimensional sphere. So in this work, the researchers regard each of these points as living in this 7-dimensional sphere, right? That's just the set of all vectors of length 1 in 8-dimensional space. And so they wanted to understand, is there some structure to this data set? And so they used, in this work, they used a tool called persistent homology, which I'm going to explain to you in detail before the end of this talk. And using this tool and some hands-on finagling with the data, together, they discovered that the densest regions of the data set concentrate around a 2-dimensional surface called a Klein bottle. And so many of you may not have seen a Klein bottle before, but a Klein bottle is an object of great affection amongst mathematicians. It's a surface with some very interesting geometric properties. So, for example, one property of this guy is that it can't live in 3-dimensional space without intersecting itself, but it can live in 4-dimensional space without intersecting itself. So the 3-dimensional picture where it intersects itself is down there. It's like you have a bottle and a long neck, and you let the neck twist around and pass inside of the bottle until it meets the bottom of the bottle. It's a Klein bottle. So they discovered that if you remove the points of least density, this guy lives, this is where the densest points live around. And so they were actually able to describe explicitly what the set of patches look like that concentrate around this Klein bottle. And I don't want to go too much into it, but roughly it's a 2D space, so you have 2 parameters describing the space. One of the parameters gives rotation of a patch, and the other parameter controls the sort of black-white distribution of along the patch. So anyway, this gave some nice understanding of statistical structure of these primitives of images. And the researchers, some of the researchers, Gunnar in particular, together with his former graduate student, Jose Perea, were able to leverage this understanding of the statistics of this data set to build a texture classifier, right? So here's an example of some textures that they considered in their paper. This is just, texture is this sort of locally constant feature in an image, right? Like my t-shirt, my shirt has a certain texture, my pants have a different texture, wood has yet another texture. And they built, I won't go into the details, but they built a classification method based on this understanding that that most things in this image patch data set are close to the Klein bottle. And it turns out that they were able to get pretty close to the state of the art using this perspective. So anyway, I think this is a nice illustration of topological data analysis driving scientific understanding and then driving applications. Now, a lot of people are working on applications now. This is sort of a fashionable thing, and many people are working, many mathematicians and computer scientists and statisticians are working together on other applications of topological data analysis. So for example, there's been work that is interesting on biophysics of proteins, especially trying to understand compressibility of proteins, on genomics and evolutionary biology, virus evolution, on astronomy, understanding the large-scale organization of galaxies in the universe, on coverage detection in wireless sensor networks, geometry problems like shape segmentation and shape comparison. And recently, there's even been some work that received some attention in the press on basketball analytics. So a lot of people are interested in trying to apply this kind of stuff. So anyway, I hope that gives you some sense of what we're trying to do here. And so now for the rest of the talk, I want to shift gears a little bit, talk about this branch of mathematics called topology that we use in this data analysis, and then show you a little bit how it gets used in one tool called persistent homology, which is amongst our most important tools. All right, so now I'm going to introduce to you topology. Topology has different types, but a very central type is what's called algebraic topology. Okay, so informally, this is the branch of math concerned with properties of geometric objects that are invariant under continuous deformations. So what do I mean by a continuous deformation? Well, for a continuous deformation of a geometric object, I allow myself to take the object. I imagine that it's maybe made of some kind of flexible rubber, and I allow myself to bend the object or twist the object or stretch it. But in continuous deformations, tearing the object or putting holes in it, puncturing it, is not allowed. Okay? The classic example of this, anytime anybody gives an introduction to topology, they have to show this example, is that if I had a coffee mug that was made of flexible elastic, I could take this guy and bend him and twist him, and eventually, if I had enough fingers and if my cup was elastic enough, I could deform it into a donut. Right? So the joke is that a topologist is a person who can't distinguish between a coffee mug and a donut. You've never heard that. So, now on the other hand, if I have a donut and a donut with two holes, which in some sense this looks like a more similar pair than the other, it turns out that I can't deform one into the other continuously. And the obstacle somehow is that there's that second hole. And so, as this second example suggests, the primary example of a property of a geometric object invariant under continuous deformations is the presence of holes in the geometric objects and the number of holes. And as such, algebraic topology is largely concerned with studying holes in geometric objects. It's interested first in formalizing the notion of a hole in a geometric object mathematically, and it turns out that to do that right takes some work, as intuitive as the notion of a hole is. Secondly, topology is interested in calculating the numbers of holes of different types in geometric objects. And third, it's interested in understanding mathematical implications of the presence of holes. And I don't want to say too much about that, but it turns out that they're really central implications mathematically of the presence of holes in geometric objects. For example, questions of whether I can solve equations on certain domains boils down to whether those domains have holes. And really, topology is a central component of modern mathematics because of these connections, but I won't say anything more about that right now. But I will say that in algebraic topology, we distinguish between different types of holes, and we define, in fact, I-dimensional holes for each non-negative integer I. Okay? How does this work? Well, some of you might find this a little bit funny, but the convention is that zero-dimensional holes are connected components of geometric objects. Okay, so for example, this pair of ovals that I drew here has two zero-dimensional holes because it has two distinct objects. All right, that's how we think of holes mathematically in this world, even though that's not always how we use the word holes in English. Okay? Secondly, a one-dimensional hole in a three-dimensional object is a hole that you can see through. Right? So the donut we think of as having a one-dimensional hole. Right? Or a slice of Swiss cheese has many one-dimensional holes. Right? And then a two-dimensional hole in a three-dimensional object is a hollow space. For instance, a tide-inflated balloon has this hollow space that traps air inside. That's a 2D hole. You can't see through it, but somehow it's a hole. Okay? So we have a formalism for counting holes in this world, and this is the formalism of Betti numbers. Okay? So intuitively, and to define this, again, takes some work mathematically, but the intuition is very simple. For a geometric object x, I define the ith Betti number of x, which I denote like this, b sub I of x, to be the number of I-dimensional holes in x. Right? Simple. It's the number of holes of ith dimension. Okay? So for example, this double-hole donut that I showed you before, I think of the donut as solid, by the way. Right? It has an inside. It has some cake inside. It has Betti 0 x equals 1 because there's one connected component. Betti 1 of x is 2 because there's two holes that I can see through. And Betti 2 of x is 0 because there are no hollow spaces that trap air inside. Okay? So that's our language for talking about numbers of holes. And let me just say that this is something that you can compute. So if my geometric object is represented in a nice enough way, discrete enough way that I can put the guy on the computer, then I can compute the number of holes, right? And up to reasonably big objects. And that's done by linear algebra techniques. Okay? So now let me turn to discussion of persistent homology, this topological tool. Okay, the main question here is how can we use the hole detection formalism of topology to develop robust computational methods for studying the qualitative features of data? That's sort of the broad question. And so persistent homology provides one of the perhaps the most prevalent answer to this question in topological data analysis. And it was introduced in the year 2000 by Edelsbrunner and his co-authors, and since then has been the subject of a lot of theoretical work and a lot of applied work also. Okay? So persistent homology produces simple descriptors of the qualitative features of data called barcodes. All right? And here's an example of a point cloud data set and an associated barcode. So a barcode is nothing but a set of closed intervals in R, and we usually, right, these are just intervals in the real line. They have a left endpoint and a right endpoint, right? And the way that we interpret this guy is that every interval corresponds to some qualitative feature of the data. Long intervals correspond to significant features. Short intervals correspond to insignificant features, or noise, if you like. Okay, in this picture, I have this large sparse ring, small dense ring. It turns out that the interval, that long one on the left corresponds to the small dense ring. The interval down here on the right, which is meant to extend beyond the slide, it's actually meant to be a long one, corresponds to the large sparse ring. Okay? So how do we define these guys? What do they mean exactly? Well, let's look at this model example to motivate this. Call this space X. This is my little cycle of point cloud data that I saw before. How can we formally detect the cycle? If we're looking at the slide, it's easy enough to see that there's a cycle there. But what if this guy sits in 30 dimensions. How do we see the cycle, right? So here's a naive idea. First, let's choose a radius, some non-negative real number, some positive real number actually, and let u of xr be the union of balls of radius r centered around the points of x. So I take every point in this point cloud data set and I put a ball around it, and I just take all of those balls. That somehow allows me to pass from a discrete object to a continuous object. Okay? So, and then the idea is to consider the first Betti number of this thickened object for some choice of this thickening parameter, r. Right? So for example, if that's x, for some choice of r, that's what u of xr might look like. And you can see that this thickened space has Betti number 1. Right? It's got one hole that you can see through. It's capturing the fact that there's that cycle there. Okay? And so that's a sort of a natural, if you know this whole counting formalism, that's a natural thing to try to do. And indeed, when x is nice enough for a good choice of the radius, this b1 of u of xr detects the cycle in the space x. Okay? And in fact, these guys are computable also in practice, but nevertheless, there's several problems with this approach. So first, there's no clear way to choose the radius. Right? You have to make this choice. How do I do it? And in fact, I'll show you there might not be a good way at all. Secondly, the invariant is unstable with respect to this Betti number count is unstable with respect to perturbation of the data or small changes in r. It might close up a hole that wasn't there if I move r a little bit. It doesn't distinguish small holes from big ones. And the invariant is very sensitive to outliers. Okay? 4 really significant problems in practice. Okay? So for example, if I have a data set like this, right, with 2 rings now, and I start constructing these unions of balls, then for a small radius parameter, I'll see the small hole, but I won't close up the big cycle, whereas if I choose a big radius parameter, I'll fill up the small cycle by the time I close up the big one. So I'll never quite see in this sort of multi-scale, multi-density setting that this has 2 features that I'm interested in. Okay? And Andrew will talk more about this later. Sensitivity to outliers is a serious issue, which we know how to deal with it. I won't tell you much about it in this talk. But if I corrupt the data with points, this messes everything up. I can get a lot of holes with a couple of small points. All right? So I'm going to talk about how to deal with problems 1 through 3. Andrew will say something about dealing with problem 4. We can deal with it, but it's beyond the scope of this talk. All right? So the solution, in short, is this. A solution is to consider not a single choice of radius r, but all choices of radius r at once. We're going to look at every one of these unions of balls for all radius parameters, and that gives us what we call a filtration. And filtration is a 1-parameter family of geometric objects. In this case, this Should I turn this guy off too? Maybe that's a good idea. All right, how about now? To tell you the truth, I was hoping to have a chance to use this. I think it's a little more fun. So, right. Okay, all right, so moving on then. So I have this point cloud data set, and I want to consider now this whole family of growing balls, right? And as this radius parameter increases, these guys grow, right? So I have this nested family of geometric objects. And the key mathematical observation which allows us to define these barcodes is that not only can we count holes in each space in a filtration individually using these Betti numbers, but in fact, we can track the holes in a consistent way across the entire filtration at once. And the algebraic formalization of this idea is persistent homology. This is what will give us the barcodes. So to give you a sense of how that goes, let's come back to this little frame-by-frame animation, and let's see what happens as the radius increases. So you see I increase the radius a little bit, and it might be hard for some of you to see, but some little holes start to appear over here. And I increase the radius a little bit more, those holes close up, but now a big hole appears. And as I continue to increase the radius, you see that this hole here kind of lives on in the different spaces. Somehow you see that it's the same hole across the range of spaces. And eventually it dies, it closes up, that hole dies. Now this other bigger hole appears, and as I continue to increase the radius parameter, this guy continues to live on for a while, right? So we see that we can track holes in a consistent way across the whole filtration. It makes sense to talk about the holes as a property of this one parameter family, not only as a property of the individual objects, okay? So using that idea, for each non-negative integer I can define a barcode, right, which I'll also denote bi of x. X is our data. And again, this is a set of closed intervals in R. So the first barcode will look like this for this data. And so, again, when that hole closes up, this interval appears. And it dies when that hole forms, that interval there appears and closes when the hole closes up. Similarly for this. So we see that each interval represents an I-dimensional cycle in the filtration. And each interval is also, via its left and right endpoints, is also recording the radii at which a cycle forms and closes up. Okay? So that's the interpretation of these guys. Okay? Now, so I'm going to wrap up here in a second. But a couple more things to say. So first, I want to just mention a few nice properties of these guys. So as maybe you've seen already, these barcodes allow us to distinguish insignificant features from significant features in the data, right? Namely, the length of the bar, it quantifies the length of the interval quantifies the significance of the corresponding feature. Secondly, we see that it's recording the size and the scale of the features. And so it turns out that the barcodes are stable with respect to perturbations of the data. Okay, and that's one of our sort of main mathematical results in this field. And lastly, these barcodes are actually computable in practice. In fact, the algorithms for this are, everything is relative, but we have pretty efficient algorithms for doing these kinds of things, and I think that's been a lot of the reason that this topic has become so popular amongst people recently. So, okay. 2 more remarks. Now, once we have barcodes, we have these representations of the holes, but where are the holes? Well, in principle, we can do further processing to find geometric representations of the significant holes. So there are computational issues sometimes, but for example, we can find this sort of nice cycle representative of this 1D cycle. And then second remark is that I really want to emphasize this. This framework for building descriptors of data via barcodes is a flexible one, and I think this is another big part of the appeal for this. I showed you one instance of this persistent homology pipeline, but this pipeline works in other settings. For example, we can build filtrations from point cloud data whose barcodes detect clusters. Yeah. Oh, time. Oh, yeah, thanks. Okay. Yeah, I'll be done in 3 minutes. So, you believe me? So we can build filtrations from point cloud data which detect clusters or flares, and we can also adapt this to detect qualitative features of functions like modes that I showed you in the beginning. Okay, and so the last thing to say is that in this field, we're always interested in hearing from people that have data and want to understand the structure of their data. So I think me or Andrew or really anybody in this field would love to hear about your data. So come talk to us if you think that this kind of stuff might be interesting or useful to you. And so that's it. Thank you.
Okay, I said to Ricardo and to Virginia and to Elio that I am a pretty bad moderator. And I already made a mistake, you know. He has already talked and I never told you anything about his CV. So I will have to tell you after his talk a little bit about his CV. So sorry about that, Mike. First of all, as you can notice, he's a quite young professor. He just got his PhD from Stanford in 2012. He worked under supervision on one of the best algebraic topologists in the world, Professor Gunnar Carlsson. And then he went last year for a year to Princeton, to the Center of Advanced Studies in Princeton for a year. You know that the best graduate students after a PhD in the US, typically they go to Princeton for 1 year or two. So he just spent a year in Princeton. And then he was one of the elected postdocs to the Institute for Applied Mathematics in Minneapolis at IMA, this important center in applied mathematics in Minneapolis. So he was one of the elected postdocs, so he's spending, in fact, 1 year at IMA this year. As you already know, he's an expert in topological data analysis, and most of his recent work has been mainly theoretical, but in the last year he has begun to think more about practical and computational questions. Finally, even as you can see, he's a quite young professor. Of course, he has been involved in several papers. But topological data analysis is really a new field in topology, in computer sciences and statistics. But certainly, let me just mention one of his last papers, is studying the shape of data using topology. Okay, so now I present you to Mike, finally.